This has been a great visit so far. It's short, but really sweet. And these are some of my favorite kinds of talks to give with a joint audience. But I can tell you from past experience that I'll almost surely offend everyone at some point. But it's not by design. But I think that's sort of the nature of interdisciplinary talks, right? So it is meant to be a little bit tutorial and certainly an overview. So hence the title. And let's just get started. So it's no surprise, right, that let me figure my pen out here. All right. That the Earth is pretty complicated, right? And it's physical, biological interactions. And so the things that got me interested in these kind of problems are illustrated, if I can do it on this little screen here, by these animations. So in the upper left, you'll see sea surface temperature, and this is a visualization from satellite observations. These are actually clouds and precipitation based on a simulation model, but still it's fairly realistic. And then these are ocean color observations, which are a proxy for phytoplankton in the ocean. And they're not meant to be synced up or anything, so I'm not that clever with my animation techniques. But I want to point out a couple features. In particular, I want you to look at the tropical Pacific. And if you look at the tropical Pacific and the sea surface temperatures, you see those little waves that are propagating towards the west. Okay. It's associated with the tropical warm pool in the Pacific Ocean, which is very much a climate driver and weather driver in many respects across the globe. You'll also see associated with that in the atmosphere here some other little clusters that happen on the sort of same time and spatial scales. And then perhaps more surprisingly to you is that you'll notice the similar features in the biological representation from the ocean color. And you'll see those little waves propagating throughout. You'll also see features here like the sensitivity to light in the phytoplankton. But it's this combination, this interaction across three fairly diverse systems that are coupled here that drive the interest in spatial temporal dynamics for most of us. Okay? So we have a multivariate space-time system operating on many scales. And even on smaller scales, you can see patterns that, for example, this is showing the spread of an invasive species, a Eurasian collar dove, throughout the 1980s into the future. This is showing a raccoon rabies epidemic in Connecticut that happened in the 1990s. And so once again, what do you see here? You see dynamical interaction. You see changes in space through time. Okay? Even on a smaller scale, and this is actually a simulation of a stochastic cellular automata of a SIR epidemic, susceptible, infected, recovered, for multiple states. And the thing to point out here is not that this is a 60s psychedelic remix, but rather that notice that you see these propagating wavefronts, you see diffusion going on, you see interaction going on across many different components of that system. Okay? Very much a dynamical process, in many ways operating on the same kinds of, with the same kinds of behaviors that we saw in those first animations. Okay. So the commonality here is dynamics. In other words, how spatial components interact through time. I mean, that's my definition. You know, I'll mention a little bit later how statisticians sort of often view dynamics, which is completely different from this in many respects. But it's how the world works. It's things like diffusion, advection, growth processes, birth-death processes, waves, frontal behavior. All this stuff is what makes these processes interesting across time and space. The other thing to point out is that there are different scales of interaction going on here, and the processes are interacting with each other in various ways. So this is going to be an overview talk, and I'm going to really give you some examples. Okay? Each of these examples, really, there's a more detailed talk associated with, but that's not the point of this particular one. And I am going to focus on the dynamic perspective of space-time, but I'm going to give you the other sort of marginal perspective as well. And I'm going to focus a lot on this notion of hierarchical modeling, because I think to capture much of the realism that's necessary to model these systems, we have to delve, to get that complexity, we have to start thinking hierarchically, or at least it helps to. And then, time permitting, I'll go into what I think is sort of, in statistics, is kind of the current state of the art in terms of interest, and that's in nonlinear dynamical spatio-temporal models. And in particular, I'll talk about what we call general quadratic nonlinearity and some ways to think about estimation and prediction in that context. So first, why do we do spatial-temporal modeling in statistics? So those of you who are in applied math, you may have a different motivation for why you do spatial-temporal modeling. In statistics, it usually comes into one of four categories. Either we're going to predict in space, we're going to interpolate, and we're going to help that in some way by having the time information. Okay. We might predict in time, or you might call that a forecast, forward in time. We might assimilate observations with deterministic models. That, again, typically relates to both of these things, both the interpolation and the forecasting. Or we may want to do inference on parameters or controlling properties of this system. So maybe, does this habitat variable really influence the density-dependent growth of some ecological process, for example? Okay. So again, for this talk, I want to make a distinction between stochastic and statistical. Because to me, at least, the former is talking about random structures in models, whereas the latter is really about estimation, inference, and prediction in the presence of data. Okay? And I think in some sense, this is the difference between a statistician's view of space-time modeling and an applied mathematician's view of space-time modeling. Not that there aren't overlaps between those, there certainly are. Okay, so why were we going to do this? I'm going to give you a motivating example, and I'll come back to this at the end. So a few years ago, we were started working on a project to consider the lower trophic ocean ecosystem. And in particular, we were interested in whether or not we could help link the dynamics in the ocean with the biology in the ocean to better understand and predict what was happening on different scales. And so this is the coastal Gulf of Alaska. And if I showed you that animation again from the first slide, it was up in obviously in Alaska. But you'll see that there was a very strong phytoplankton bloom that happens every year, actually twice a year, in that region. Okay, and this is, we have satellite information from the ocean color, and these are aggregates of 8-day averages. And you can see even at 8-day averages, there are big gaps in the data here. So one of the first problems that one gets when you deal with this is, what if something interesting is happening in that big gappy region? And why is there a gappy region? Well, most likely that gap is because there are clouds there. Okay? If you're looking at ocean color, you got to be able to see the ocean. If there are clouds, and it's the coastal Gulf of Alaska, if you've been there, you know it's cloudy a lot, right? So we have to have a way to deal with that. So, I think I lost my microphone. So can you hear me? Sorry. So the data is gappy, and it also turns out to be the case that there's a lot of uncertainty in these data. Okay, some satellite data, like sea surface temperature, is quite accurate. Other data, like this biological data, is actually very inaccurate, almost 100% inaccurate in certain regions and times. So we want to deal with that. So what's the underlying system? Well, this is a very simplified version of this system. It's basically a glorified predator-prey system. This is just a very simplified version with 4 components. There are nutrients. So in the presence of light, the nutrients are then food for the phytoplankton. The phytoplankton bloom up. Okay, that's this blue or the red line here. Okay, they use up the nutrients. When the phytoplankton population increases, the zooplankton feed on them. The phytoplankton population drops down. Eventually, there's a density-dependent relationship there. Without the phytoplankton, the zooplankton die off. That all drops down to SpongeBob at the surface and as detritus, and then some mixing event comes along or upwelling. The nutrients go to the surface, there's light, and the whole process repeats itself. And there are usually 2 blooms a year. There's a spring bloom and a fall bloom in this region. This is a simplified set of partial differential equations that describe that. Don't pay any attention to that now, other than just note that it's fairly complicated. In reality, this is obviously a three-dimensional system, and there are a lot more terms involved than these, if you really modeled it correctly. Interesting stuff has happened with my screen here. Hold on a second. I have soccer practice. I coach high school soccer, so that has nothing to do with this talk. I really don't know what happened there. Does anybody know what happened? There we go. All right. I think the battery must be on. Yeah, so this is not working. Yeah, so I'm going to lose the mic because it's not working. So one time, not too long ago, I gave this talk and the power went off. And so I had to describe all these pictures. It's been a lot worse. Okay, so what helps here is that there's an interaction between the physics, what's going on in the ocean, and the biology. And you can see that very clearly. This is from a simulation, but look at the colors here show you the sea surface height, and then this shows you the chlorophyll, which is related to phytoplankton. And notice the similarities just visually. There's a strong dependence between this map and that map, right? So obviously there's this relationship between the physics and the biology. Not surprising, I showed you that in the first animation. So we ought to be able to use that. So we want to be able to use the fact that we have this multivariate interacting process, these interacting processes in space and time, even if it's a nonlinear, highly uncertain system. Okay, so there's model uncertainty here. As I mentioned, the models are way more complicated than what I wrote down. There's parameter uncertainty. Even in these simple models, things like mortality and grazing rates aren't known very well from the data. And can we estimate those? That's one of the questions of interest here. Data availability. There is a little bit of in situ data, not much. Okay, it's very difficult to get zooplankton data. Somebody actually has to count those. That's not easy. Satellite data is okay, but it's gappy and not so good. So the goal of today's presentation ultimately will be, can we use that information that we have to learn something about what's going on with the phytoplankton fields that I showed you before? Okay. And we have to have a way to think about that. So what do statisticians do? Well, there's two approaches to this kind of a problem. One is what I would call descriptive or marginal. And in that sense, what we're doing is we're really modeling the second moment behavior, right? It's the covariances. We're going to assume everything's Gaussian essentially or effectively, or at least well captured by the second moment. We're going to think about basically doing kriging, if you're familiar with that, or optimal interpolation based on covariances. The problem with that is that, first of all, it's really difficult to capture realistic behavior, clearly not going to be appropriate for highly nonlinear systems. Second of all, multiple processes can actually imply the same kind of covariance structure. That might be okay, it might not. So the other approach, the one that I'll talk about today, is thinking about it dynamically or conditionally. Okay. And so this is the difference between how spatial statisticians view the world and how time series people view the world, in some sense. And so in other words, we're going to say current values of the process affect what's going to happen in the future. And I think that's much closer to how these processes really evolve, how we think about them as scientists and practitioners. And the other thing that makes this nice is that because that's how we think about them, we can actually use a priori information somehow, much more easily than we can up here. I don't know about you, but it's really difficult for me to think about covariances. I mean, I know what covariances are, of course, but it's hard for me to think what prior information is about covariance. But I can think about means. It's easy to think about means. So I like to think about that from that perspective. Okay, so let me give you a little bit of, I had to throw some equations on somewhere, right? So this is really to illustrate just a point. And this goes way back. And this is just a reaction diffusion equation. It's got the change in time. There's the diffusion term with spread. You can think about this as a growth term. And it's stochastic, so there's some random forcing. And under the right conditions, you can show, and people have shown for a long time, that you can get a correlation function analytically from this. Okay? And there are other classes of stochastic PDEs, of course, that you can do that. And this has nice properties. You get nice decay in space and in time with distance and with time lag. And that's what you would expect to see. And you can even, this is showing that. Here's the decay in space and decay in temporal lag. And you can see if you simulate from this, you get properties that you would expect. There's an initial condition here, all zeros except for the middle. If you don't have much noise, you get the usual sort of decay that you might see in a diffusion process. If you add enough noise, you get interesting things because the noise becomes, starts having its own, is affected by the dynamics as well. So that's pretty standard and looks fairly realistic for certain kinds of one-dimensional processes. All right. But, so even though you can do that, you can develop these classes of models, you can't do it very easily or at all for a lot of the realistic processes that we just have talked about. So perhaps we could think about these conditional models as a way to do that instead. And before I do that, I want to show you that it's not so unreasonable to think about discrete time, discrete space dynamic models as way as surrogates for this kind of process. And you'll see why we end up going in that direction here in a second. So before I do that, I have to tell you what a linear space-time dynamic model looks like. So this is discrete space, discrete time. So here's a vector of observations of dimension mt, so it could change with time. Y is our process, unobserved process vector. These are spatial locations, there's n of those, and again at time t. And so what we'd like to do, here's an observation model. So if you're used to in engineering, control engineering, or in time series, you've seen these state space models many, many times, right? That's all this is. So this observation gets related to the process through this observation matrix, which could handle dimension reduction. It can do a lot of different things. Additive errors typically. This is a first order model here, a Markovian model, vector autoregression, you can call it whatever you want. The important part of this is the transition or propagator, transition operator or propagator matrix M, which will end up controlling the dynamics. And the noise process, we're going to assume is Gaussian for this simple model. So the important part for us is really this M, this propagator. And what does that do? It just tells you how the process at previous time at different locations interact linearly to give you the new process. Okay? You think of it as a smoother, or you can think about it as a propagator. It's up to you. Okay? So the problem with that in space-time systems typically is that n is large. The number of spatial locations is large relative to the number of times you have. And so n-squared parameters can be really super difficult to estimate. Okay, well. So even in linear systems in high dimensions, this is problematic. Okay. So traditionally, statisticians have a view about dynamics as just being fairly simple things that we move through time. So we could try like univariate autoregressive models. Okay, that might be all right in certain processes. Random walks even. But the kinds of dynamics that I showed you really don't work that way. Right? There's more going on. There really is interaction going on. So maybe there are some other parameterizations that we should consider. And so the common ground here is that that differential equation that I described before, if we discretize it, will look just like that difference equation, or that vector autoregression model that I showed you. And so here's the key, and I underlined it and made it red. I don't want to solve that differential equation. I want to motivate a statistical model parameterization by that differential equation. So it's a motivation, not a solution, if that makes sense. And hopefully you'll see what I mean by that. So what a simple example would be if I took that differential equation I showed you before in one dimension, and I just did a finite differencing on it. Okay, first order in time, second order in space. If you do that, and sometimes I write this slide out and it's boring and everything, but basically you get a tridiagonal operator for your propagator, right? So the nearest neighbors are important, as well as the same location at the previous time. Okay, and then there's some boundary stuff that I ignored here. So the point is that M is highly structured. And so knowing that I want this kind of property, I already know something a priori. Right? If I know that I have sort of diffusive behavior and sort of a reaction type model here, what I could do is just assume that all those off-diagonal elements are 0, but then just estimate the n order n observations that correspond to those 3 diagonals. So already I've done a fairly substantial dimension reduction, but it's in the parameter space. And it's simply by just assuming I knew a little bit about the process. So it's sort of obvious, right? Does that work? Well, you know, if you take David's multivariate time series class, I'm sure you'll have seen something like this. You can get the spatial covariance at any time lag by this formula here, okay? Assuming you know what the lag covariance is at lag 0, which if you know m and the error covariance you can do this. And if you do, what does it look like? Well, relative to the continuous solution, big surprise, it looks really similar except right towards the origin, right? Obviously, if you make your discretization fine enough, you're going to get nice behavior at the origin as well. But certainly, for most kinds of dynamic processes, these two things, you wouldn't see the difference in a fairly noisy environment. Okay, so I took something that I knew for sure and I made it worse. So why would I ever do that? Why would this ever be done other than it's easier to work with in some sense, but it's really not. So this is the key, okay? We don't really ever know the real form of our dynamics in the kinds of systems that I described. We know something about how they work, but we don't really know. It's not really an advection diffusion equation, right? It might show some of those properties, but it's more complicated than that, okay? So here's the idea. You use a simpler model, maybe it's a discretized model, like I said, but you motivate the parameterization of that model by something that you knew about the dynamics. And if you let those parameters themselves be structured, or random fields, or time series, so there's some sort of dependence in them, typically, you're going to borrow strength, have effectively fewer numbers of parameters to estimate, and have the same ability to model systems that are way more complicated than you could solve analytically. Okay? So, that sounds great, but how do you really do that? I mean, how do you estimate or calibrate these parameters? And that's the key. And you do it through conditioning. It's much easier if you think about this in a hierarchical context. So I started using this slide about 15 years ago, and I still use it periodically because if you're not familiar with this, you can see it's really pretty straightforward. If I have a joint distribution, you know, from probability, elementary probability, I can write this joint distribution as a conditional distribution of one given all the others, times the distribution of the next one given all the others, times ultimately the marginal distribution of the last one. Okay, so why does that make a difference? Well, my colleague and mentor, Mark Berliner, back in the mid-90s, had a very simple realization that was obvious, but for dynamical modeling of complicated systems hadn't really been done yet. Just think about just splitting up your whole modeling system into 3 basic components: data, process, and parameters. And then I have a data model, which is like what I showed you before in the observation model. And so why is that helpful? It's helpful because data, if I condition on the process and the parameters, the leftover stuff is usually pretty simple, right? As opposed to trying to make a likelihood that has all that weird, complicated, nonlinear space-time dependence in it. Now all I have to do is think about the likelihood given that I knew the real complicated process. And so that's usually just like measurement error, errors of support of space and time, something like that. Then I can focus my process modeling on the actual process. I don't have to try to confound the modeling of the data and the process together. I can put the emphasis here. And then here's the key to today's talk, is that I also then can model the parameters statistically in terms of their own processes. So maybe my parameters are spatial random fields, or maybe they're space-time processes themselves. Okay. And ultimately, I want to do inference on these things given the data. And so Bayes' rule lets me do that, and Markov chain Monte Carlo or other sorts of fancy Monte Carlo techniques allow me to sample from that distribution. So that's the idea. So going back, so what kinds of things will we parameterize our transition operator for? Well, most of the kinds of linear dynamics that you see in the environmental and biological processes fall into sort of 3 categories, I would say. There's movement, in terms of what I would call, I guess, advection, or moving along. The whole blob is moving up to the upper right. There's some sort of diffusion typically. There's a spread of this, okay? And then there might be some growth. Well, the first two of those things are easily accommodated by recognizing that the width of the transition operator controls the diffusion, and the asymmetry of that transition operator controls the speed of propagation. So if I can parameterize my transition operator in terms of these two notions, in terms of thinking about the width of the operator at any given location and its asymmetry, then I can model this kind of behavior. Okay. I can also do more complicated things if I'm willing to have multimodal operators. So that's pretty cool. So how would I do that? Well, I have the same modeling system I showed you before. The only thing that's different is I let the parameter M matrix here depend on these, the transition operator depend on these parameters. And so then I put information in my model structure for these things. And so rather than go through a lot of that, I just want to show you an example where we did this. And I know you can't see this really well, but let me describe. So when you have thunderstorms that pop up in the summer and you're worried about whether or not this severe thunderstorm is going to hit your area, they pop up on TV and they say, the storm's going to hit Ithaca in 25 minutes, right, or whatever. And so take shelter or put your car in the garage or whatever you want to do with it. And so this is an example, and this is some data from Sydney, Australia, that was collected around the Olympic time in 2000. And what we have here is radar imagery of storms moving through time down this way. And there's a lot more data that I don't show you that came before this. But notice that these data, that you see these blobs here, the two blobs that are at the top, they're all moving kind of northward and northeastward, and there's kind of a merging of the blob. There's some change of intensity. So what we did is we just fit that simple advection diffusion model to that. And we parameterized the transition operator as by the width of a kernel. So in other words, how wide the neighborhood was versus how skewed it was. Okay? And so basically there were two parameters that controlled that, and we treated those as random fields themselves. So that meant there was some borrowing of strength across all these pixels. You can tell there's quite a few of these things. But very simple model, but highly parameterized. And so what you get at the end of the day, this shows you what was the posterior, not of the movement, but of the suggested movement by the shift of that transition operator. So if you see an arrow here pointing up this way, it says that it shifts up in that direction, so it's skewed that direction, and if it's bigger, then it's more likely to move faster. Okay. So it's an inverse problem, but we highly parameterize transition operator. And so did it work? Well, this is the posterior mean from the Bayesian model estimation, and you can be the judge whether you think it worked or not. But it did a fairly decent job of modeling behavior that's not just a linear extrapolation. And you can see that here because the speed of, if you had a blob here, it's going to move faster than a blob that's here. Traditionally what happens is that one models the movement of a blob just as an arrow based on the last few times and just assumes it's going to do that. Well, there's more to it than that. And this shows you the uncertainty in those realizations and then the posterior standard deviation. So in other words, it was pretty effective for a very simple model. Okay. So that's a linear model. And I think you could beat those linear models to death, and we've done them in spectral space and Galerkin space, and it all kind of works the same. The bottom line is if you have a reasonable amount of data and some prior knowledge, you can model those in even high dimensions and get fairly good uncertainty predictions. Okay. So the next question is, can you do the same sort of thing in nonlinear systems? And what challenges are involved with that? Okay. And so the three primary ways, I think, to model space-time dynamics in statistics is either through time-varying parameters like threshold models, or increasingly, and I'm not going to talk about it here, individual or agent-based models, or what I'm going to talk about today is a parameterization that we call general quadratic nonlinearity. And so this is a class of parametric dynamical models. Okay. And the thing about this is, as you're going to see, the problem with this ultimately comes down to the cursive dimensionality and how we deal with it. So if the parameter space was bad in the linear model, just wait and see it now. It's going to be horrible. So first of all, what does it mean? What does quadratic nonlinearity mean? Well, if you look at this simple reaction diffusion equation, this diffusion part is inherently linear, okay? But notice the interaction between y and this functional version of y here in the density-dependent growth term, okay? This is definitely what I would call generally quadratic nonlinear, because there's a transformation of y times y, okay? In the usual traditional simple epidemic model, SIR model, the interaction between susceptibles and infecteds is nonlinear. It makes sense, right? If an infected person comes in contact with a susceptible, there's a chance that there's going to be an infection. But the rest of the system is linear. Okay? So that's a real world process. I could keep showing you more. It's harder to find good examples of things that aren't quadratically nonlinear than are. Almost all of the, other than in turbulent kind of processes, most things are quadratically nonlinear. And so here's the system that's related to what I'm going to talk about later, and this coupled ecosystem example. So you can see it's hard to mess around with all this. The real nonlinearity comes here again. Okay, this is the quadratic nonlinearity part of this predator-prey type model. Okay. So what we did is we wanted to come up with a way to parameterize that, and so this looks way worse than it is. So let me describe it. So this is some process y at time t at some location I, spatial location. Here's the linear part that we already talked about. So this is just saying linear association between the previous time at all the locations by these parameters. This is the interesting part. This is the quadratic nonlinear part. So now, for this location I, there's a possibility that all the other dyadic combinations interact to influence what's going on. But it's more than that. There's a parameter that controls that, but then we're also allowing for the possibility, and this is crucial in many problems, that there's a transformation of one of these. Okay, so it's this transformation of y, which is why we call this generally quadratic, like kind of like generalized linear models. And there's parameters that control that. And it turns out that that's really can be important for various reasons. It can accommodate growth processes, but also it can allow you to keep these models from blowing up. If there's a, well, I won't go into it, but you can show that without that, in most cases, these things will have a finite time blow up, okay, if that matters. The problem is there's order n cubed parameters here, right? And if I couldn't estimate n squared parameters, typically, how am I going to estimate n cubed parameters? And I can't really, I can't do it. Here's a matrix version of this, which isn't so important, but the formulation is what's important. Okay, couple points. One point is, these can be multivariate. I could have strung a bunch of different variables together. That's okay, but it just makes it worse. I just have more parameters to estimate. Okay. So there's too many parameters. A couple things we can do. We can do mechanistically-motivated parameterizations, and I'll show you an example of that. So we're going to, again, use models to help define which parameters should be 0 and which ones shouldn't, and then only estimate the ones that shouldn't be. We can do reduced rank models, low order models, so maybe we'll assume that y can be modeled spectrally in this terms of a couple decompositions. Maybe these are the ones that are going to interact quadratically nonlinearly, and these smaller scales don't, or maybe there's interaction across these, but we could do it that way. We could also take advantage of hierarchical statistical things like stochastic search variable selection. I'll describe that. And then hopefully I'll have time to suggest that we could also use emulator-assisted prior specification, whatever that means. Okay. So here's the first example. This is a reaction diffusion model, density-dependent growth, as I mentioned before. So again, this linear part of the model is easy. We already know that this contributes to those nearest neighbor parameterization. And then this part is nice because the only interactions that are important here, the only dyadic interactions, are at the same spatial location. So again, we're on order n parameters now because we only have to estimate these parameters for just at each location, not every possible combination. So that mechanistically motivated model is actually, it is quadratically nonlinear, but it's highly structured. Most of those V parameters I showed you before are 0. And so here was the first example that we did with that. We took that model and we allowed the diffusion coefficients and the growth parameters to be spatial random fields. And then we modeled the Eurasian colored dove invasion. So what happened is that the colored dove had colonized Europe in the 1930s and then got introduced from the Bahamas into the US and South Florida in the early 1980s, and then took off, right? And it likes the same kind of habitat that ringed turtle doves have. And so it's a generalist, it likes everything, right? It's going to move. And so back when we started this, and we finished this first work in the mid-2000s, you can see where, in a second here, this ends up stopping about here, kind of where the bird was at that time. So we wanted to see if we could predict, using this methodology, the actual spread of the epidemic. And so I'm not going to show you all the results, but this is showing the prediction that clearly by now most of this part of the region would be covered. And true enough, if you look at where these birds are now, I mean, I'm not saying it was a great prediction, but they clearly are where we said they would be and beyond, actually. And so we were able to do that with a very simplified model. Okay. The next thing is then, what if I don't really know that mechanistically motivated, I don't have that PDE. I have a system where I know that it has some behavior, but I don't really know that. And so this is what I would call a reduced rank hierarchical generalized quadratic. See, if you put enough acronyms and letters, then people think it sounds more complicated than it is. No, really. These aren't all useful, but space-time dynamic model, generalized quadratic nonlinear, hierarchical, reduced rank. So I have a data model like I described before. There's nothing different about that. This is the part that's important. So I take my process and I decompose it spectrally into different coefficients. And you could pick your favorite, so I'm going to make this point, you can pick your favorite way to do that dimension reduction. You might have your favorite basis. It might be a spline basis. I might like empirical orthogonal functions. You might like polynomials. It doesn't really matter. It might matter for the given system that you're in, but I'm not going to say that there's one that's always going to be better than the other. I am going to say that I like to decompose this into two components, one with smaller scales and one with larger scales. And I'm not saying that's always the best thing to do, but it works pretty well. And then I'm going to let the larger scales evolve quadratically nonlinear. That's just the vector form of that, with Gaussian errors. So it's not marginally alpha is not Gaussian, but conditionally it is. So that's easy to work with. And then I'll put some sort of distribution on the small scales, and that's not important for this talk, so I won't go into it. And then the question is, what do I do with all those parameters? How do I specify the priors for those things? And so the first thing that we did was use a standard approach that's been around for a while now that's really conducive to hierarchical modeling, and that is stochastic search variable selection. And the idea is super simple and super powerful, and it's just saying each of those parameters now is going to be have a mixture prior, and that mixture prior is going to depend on whether there's a coefficient here that says, is this parameter in the model or not? If it's in the model, it has this prior distribution. If it's not, this formulation assumes there's still some chance that it's non-zero. Okay, there are other formulations here, a spike and slab, where this would actually be a zero mixture. There's also the Bayesian lasso, which also shrinks the parameters. But this is fairly simple and fairly easy to use. You then put it's hierarchical, so you then put a probability distribution on these, whether it's in the model or not. And this prior specification is powerful because if you know something about whether the parameter should be in the model or not, like maybe from some science, you could use that here. You could build dependence. You could put prior notions of dependence in your model. So this is pretty good. I mean, this turns out to be highly effective because it lets you shrink most of the parameters to zero. Okay. Now, I'm not naive enough to think that I'm exploring the entire parameter space when I do this, but I do anticipate that I'm at least exploring some good ones. Okay. And so here's an example where we've used this. And this is related to the long lead prediction of sea surface temperature, which is important in the Pacific for predicting El Nino events. And so say I've got sea surface temperatures up through March of 1997, which is here. Can I predict what's going to happen in October of that year? Okay. And notice what happens when you go down this way, and you can see it in the animation. You'll see this rapid, nonlinear growth, effectively, although linear is not horrible. But you see this rapid growth into what was one of the most powerful El Ninos of all time. It dramatically affected the world's weather that year. Okay. And you can see its evolution here, followed by a La Nina cold period. Okay, so El Nino just means warmer than normal. La Nina means colder than normal. So that's an important thing to do. So in this case, we've got 2,500 pixels in each of these things, 300 times, fairly large dimensional data set. But the key is that most of the dynamics is happening on a lower dimensional manifold here. And in fact, I can do a fairly decent job by some naive projection onto spatial principal components or empirical orthogonal functions or Carhoon and the lab basis, whatever your favorite discipline or your discipline, you'll call them something different. But that's all these are. They're empirical basis sets from singular value decomposition. So I have 10 of those and then small scale stuff for 10 of them. I can do this really easily in a Markov chain Monte Carlo fashion. And so does it work? Well, just to show that the difference between the quadratically nonlinear and the linear model, these are the observations. This is the posterior mean, 7 months in the future. And you might think this is horrible. This actually is not a bad forecast for this. If you average this like people do, it turns out it's not a horrible forecast. But this one's better. And more importantly, the uncertainty, these are the pixelized 97 and 2.5 percentiles. This captures the real world behavior much better than this does. So one of the important points about modeling real world processes in statistics with nonlinear models is that you're more than likely going to capture the uncertainty more realistically if it's truly a nonlinear process. And this shows that too. So that worked out pretty well. Okay. So I know we've got, we don't have a ton of time left, but I do want to, we'll finish on time. I want to show you the last of these things, which in some sense is maybe the most powerful, and sort of bridges the gap a little bit between applied math and statistics. And that is what I would call an emulator-based prior specification. So what I mean by that is, if I have a big, complicated deterministic model that I want to combine with real observations to get a better understanding of what's going on at a snapshot in time, in meteorology and oceanography and other disciplines, this is called data assimilation. So we mix a deterministic model with observations, and this is how they generate initial conditions for the next forecast, say, in a forecast model of the atmosphere. So what we're going to do is we're going to build a statistical model for that deterministic model, which we'll call an emulator or a surrogate, okay? And then use that in this format. But I'm going to do it in this whole Bayesian hierarchical framework using the quadratic nonlinear formulation. And I'll show you what I mean by that. First of all, what's an emulator? So basically, this has been around a long time, but in statistics, it's used to basically build a statistical model for a simulator. And the reason it was done is mainly to do parameter estimation and calibration. So if I can only run a big, complicated simulator a few times, I'll pick some parameter values, get an output, and then sort of fit a response surface to that output given the parameters. And basically, this is a spatial statistics problem or a second-order modeling problem. And typically, people assume they're Gaussian processes. That surface is a Gaussian process, and so I can interpolate based on usual sort of spatial statistics things. And if you do it in a Bayesian context, then that's what Kennedy and Hagen did. And it's been very successful across all sorts of computer experiments. We favor what we would call a first-order emulator, which is for highly nonlinear systems typically. And basically, you'll see what that means is that we're going to just do a more dynamically based surrogate model. Okay. So I know this is a complicated slide, but it's not really that bad. I have a matrix of inputs. So each of these are input vectors, okay? And so there's k different input vectors. So say you pick parameter 1 to be 3, and I pick it for 4, so yours is 3, and the second one's 4, okay? And we keep doing that. And for each of those, we run our computer model, our simulator model, and we get an output vector y, okay? That output vector y, those are all strung together to a matrix. We do a singular value decomposition of that matrix, okay? And here's the key. First of all, most singular value decompositions can be reduced in dimension, right? Because most of the variability is accommodated by a few of the singular vectors. If you can do that, great. You don't have to. Then here's the key. We're going to model the right singular vectors as a function of our parameters, or as our inputs. Okay? The thetas here correspond to the model. So this is a statistical model for what is really a deterministic thing, right? And so why is that cool? Well, it's cool because we know how to build statistical models. And once I have that, if I have a model for V, I can, for any new input W, I can tell you what Y should be, in principle. Okay. So the question is, what sort of models should I use for this? And if you're a statistical learner person, you might use random forest or Normant or whatever your favorite tool is. You might even be able to get away with a linear model. You know, who knows? But what we wanted to do was not do a calibration, but we wanted to use this in a dynamical context. So we want to actually say what's happening with yt given the previous value. So our input vector now are not parameters, they're the previous value of the process. So I am really building a first order movement or transition model from my process based on the simulation data. And again, I could do any kind of models to do that, to build those models, and that's where statistical learning would come into play. But what I'm going to say is I'm going to say I could use that as a prior distribution and make this whole thing Bayesian and at least account for the uncertainty associated with that. Okay. And so, in particular, I would like to say, again, this is what I showed you before. This is my reduced dimension. Okay, these are like the singular vectors, or singular values. But here's the key, is that I'm going to model those right singular vectors as quadratically nonlinear evolution as a quadratically nonlinear. So if I can fit that offline, that becomes, those parameter estimates are given by this prior mean. I can put some uncertainty around that. And now I can do really high dimensional simulations of a complicated system with a fairly simple model. Okay. And so to finish up, let me show you the example. So I started with this, I'll finish it. Okay. This is trying to predict that chlorophyll ocean color field that I showed you before. So I want to combine some of the data I have from satellites with a fairly complicated high dimensional ocean model, okay, that has a coupled ocean atmosphere and biosphere interaction going on. It's called the ROMS MVCD FE model. Okay. I'm going to assume that I'm going to emulate that model's evolution by a quadratic nonlinear process, and I'm going to only consider the sea surface height, the sea surface temperature, and the phytoplankton. So I have those are all space-time fields, so it's multivariate, spatial-temporal, nonlinear system. Okay. And what do I want to do? I want to predict spatial fields of the ocean color or the primary production or the phytoplankton, whatever you want to call it, given the satellite data and that ocean output data. So I have 4 years that I've trained this on 8-day averages, and I'm going to predict this, train on this, and I'm going to predict in the 2002 year. So just to emphasize, I have 3 data vectors, 3 process vectors. The rank reduction here is on order 10 to the 5th to 10, so a lot of dimension reduction. Nonlinear emulator based on 7 singular vectors, and then a little bit about the non-dynamic ones, but that's not so important. Let me show you the results. So I showed you these 3 ocean color images from the satellite earlier. And remember the big gaps in them. Okay. This is the posterior mean and then the posterior standard deviation. So the important part of this is if you look at this eddy here, associated with an eddy in which there was a phytoplankton bloom. Okay. So there's no way that a linear model would have been able to capture this bloom, right? That's a nonlinear type thing. First of all, it's an eddy, so there's nonlinear dynamics going on that way. Second of all, there's a growth process going on, and linear models can't really do that, right, unless they're unstable. So how did that happen? How did I get, there's no data to speak of in that component that shows those things, right? And the reason why it worked was, one, because the statistical model was flexible enough to allow nonlinear behavior. But second is because we used the sea surface temperature information that was linked to the phytoplankton, which we did have, right? We had sea surface temperature information from the model output. But there was, I'm not showing it here, but there was more information gained here than there would have been in that deterministic model, right? And so that to us was pretty cool. Do we know that it really happened? No. There's no way to know, right? There's no real data. All I know is that this is here, and this is a lot different than if I looked at the data by itself, where I can't see anything, or the computer model by itself, which I see a hint of this, but nothing like this, okay? So should I be concerned about that? Well, maybe, but I also have uncertainty measures here, right? The uncertainty measures are telling me that you're uncertain about this, okay? So that might be there, but be careful. The other thing I see is that the uncertainty really is not that it's there, it's much more that the gradient of the process. And if you know much about nonlinear dynamics, you know that it's the gradients that are the harder part of it, right? That's the important part. And that's what it's telling us, is that you're most uncertain about how nonlinear that really is, okay? So anyway, we found that was pretty cool. We like those results. So I'll finish up. These are complicated kinds of processes with lots of interactions. Whether you're into ocean biology or bird migration or something completely different, there are things that are linking those together, right? There are kinds of processes that we can learn about from one that might help us model another one, okay? Additional information is important. We don't want to throw the baby out with the bathwater, so to speak, right? If you know something about a complicated system, you should use it, because you won't have the data to relearn empirically all that's going on. You know, the days of being able to do that in statistics are over in high dimensions, right? It's sort of the antithesis of statistical learning, right? It's augmentation rather than learning. Hierarchical specifications are crucial for this. Mechanistic motivations, and then I talked about quadratic nonlinearity. You can use these things don't have to just be Gaussian. You can use other kinds of error structures if you're willing to put up with the computational burden. And I didn't talk anything here about some of the other things that we and others are working on with individual-based models and other formulations. A lot of stuff to be done here. The theory is woefully weak, and even the empirical stuff is still pretty weak. And the computational burdens are enormous, but I think doable at the end of the day. So this is a useless slide because it's totally illegible. In principle, there's a bunch of references on that slide. Okay. Thank you.